Hello viewers, welcome to my channel KK Concepts of Electrical Engineering.
Application of Poisson's equation on vacuum tube or vacuum diode. The vacuum diode is a tube version of a semiconductor diode. It consists of cathode and anode separated by suitably apart inside a highly evacuated sealed glass envelope. The cathode can be heated either directly or indirectly. When a positive potential V is applied to the anode and the cathode is heated, the electrons are emitted from the cathode and these are attracted towards the anode, resulting in anode current. However, the number of electrons reaches the anode is dependent on the anode voltage. If the electrons cannot reach the anode because of the force of the repulsion among themselves, they turn to a cluster around the cathode, forming a space charge. Because of this space charge, there is volume charge distribution, and hence the field inside the tube rho v is not equals to 0. So we cannot apply the Laplace equation. We need to go for the Poisson's equation, that is del square v equals to minus rho v by epsilon naught. V equals to 0 at x equals to 0 and v equals to v1 at x equals to x1. But when x equals to 0, electric field intensity equals to minus dV by dx equals to 0. Now taking this rectangular coordinate, dou square v by dou x square plus dou square v by dou y square plus dou square v by dou z square equals to 0. But in this case, this is equals to minus rho v by epsilon naught, since we have applied this Poisson's equation. V is dependent on x only, so these two terms will be equals to 0. Then dou square v by dou x square equals to minus rho v by epsilon naught. Let this be equation number 1. Let m is the mass of the electron, E is the charge of the electron, then kinetic energy of the electron is given by half mv square, where v is the velocity of the electron, ev. This is the energy required. Half mv square equals to ev. Let this be question number 2. And the continuous stream of electrons consists of a current. Let J denotes the current density, that equals to minus rho v into v amps per meter cube. Let this be equation number 3. Then from 2 and 3 we get rho v equals to minus j square root of m by 2 ev. We know the value of rho v and this is substituted in equation number 1. Then we are going to get dou square v by dou x square equals to rho v is this value, so minus of minus plus, then j square root of m by 2 ev divided by epsilon naught. Integrating on both sides, dou v by dou x equals to 2 square root of j by epsilon naught square root of m by 2 ev plus a. When v equals to 0 at x equals to 0, e equals to minus dv by dx, which equals to 0. Now substituting this in the equation, now we are going to get then a equals to 0. Now again integrating this equation, we are going to get 4 by 3 v to the power of 3 by 4, which equals to 2 j by epsilon naught square root m by 2e of x plus Again, applying the boundary conditions this, then you are going to get then b equals to 0 again. If we simplify this, then v equals to 3 by 2 square root of j by epsilon naught, and again square root of m by 2e whole to the power of 4 by 3 x to the power of 4 by 3. Let this be question number 4. Applying the boundary condition that v equals to v1 at x equals to x1. v1 equals to 3 by 2 j epsilon naught under square root of m by 2e whole to the power of 4 by 3 x equals to x1. x1 whole to the power of 4 by 3. Let this be question number 5. 4 divided by 5. We are going to get v equals to v1 x by x1 whole to the power of 4 by 3. Let this be equation number 6. x1 equals to d, that is the distance between the two plates. Anode voltage, that equals to Va. This is anode voltage. Then this equation we can write it as v equals to Va of x by d whole to the power of 4 by 3 volts. This is an equation which satisfies the boundary conditions of a vacuum tube or vacuum diode and Poisson's equation, that is delta square V equal to minus rho V by epsilon naught. So this solution is known as a unique solution or unique equation. Then if you want to plot the voltage V along x, that x equals to 0 here and x equals to x1, then this is going to rise like this. This is the equation. If this charge is not present, space charge is not present, then this is an imaginary wave. This is for rho v equals to 0, and this is for rho v is not equals to 0. Current density, it is J. I am considering the equation V1 equals to 3 by 2, that is equation number 5, and the square root of J by epsilon naught square root of m by 2e whole to the power of 4 by 3 x1 whole to the power of 4 by 3. Now solving for J, then from this you are going to get J equals to 4 by 9 epsilon naught V1 3 by 2 and under square root 2e divided by m 1 by x1 square amperes per meter square. And this relation of current density is known as Langmire space charge law. Space charge law. Current I. Now in the above equation, that is V1 equals to Va and x1 equals to d. Let A is the area of cross section. Area of cross section. Then current I equals to charge density into area. That equals to 4 by 9 A epsilon naught V1 3 by 2 divided by d square root of 2e by m amperes. And we know epsilon naught equals to 8.854 into 10 to the power of minus 12 farads per meter, and rho equals to 1.6 into 10 to the power of minus 90 coulombs, and m equals to 9.1 into 10 to the power of minus 31 kgs. Now substituting these values and simplifying this, then we are going to get I equals to 2.34 into 10 to the power of minus 6 VA 3 by 2 divided by d square amperes. Field intensity, that is E. We have E equals to minus dV by dx ux, that equals to minus ux d by dx of v x by t whole to the power of 4 by 3. This is from this unique solution. This equals to minus ux at va divided by d to the power of 4 by 3, and 4 by 3 x to the power of 4 by 3 minus 1. E equals to minus ux 4 by 3 va by d of x by d of 1 by 3 Newton per coulomb. This is negative direction of x-axis. Variation of rho v with distance. Rho v equals to minus j square root of m by 2 ev, and v equals to 3 by 2 square root of j by epsilon naught square root of m by 2e whole to the power of 4 by 3 x to the power of 4 by 3. Now this is along the x distance, and this is rho v. Rho v is proportional to x to the power of minus 2 by 3. We are going to get curve like this. This is rho v is proportional to x to the power of minus 2 by 3. As the distance increases, rho v decreases.
If you have any suggestions and queries, please mention in the comments. If you like this video, please like, share and subscribe. Thank you for watching the video. Please stay tuned for more videos.